Hey everyone. So we talked a little bit about how wires with current running through them placed in magnetic fields will feel a force. This seems like kind of a silly academic thing. It leads to wires jumping a little bit and things like that. But it actually has several really important practical applications that we can talk about by considering the torque on a loop of wire placed in a magnetic field. We'll find that this is sort of very similar to the torque felt by an electric dipole, something that we didn't really explore all that much, placed in an electric field, but also similar to the torque felt by a magnetic dipole in a magnetic field, something like a permanent bar magnet aligning itself with a magnetic field, like a compass aligning itself with a magnetic field. So to figure out the torque on a loop of wire in a magnetic field, we can draw that loop from two angles. So over here in the top left, I've drawn a side view of a loop of wire in a magnetic field. It's got a current running through it. From this side, it's a current in the clockwise direction. There's a magnetic field pointing to the right. The width of this loop is given by W. Its height is given by L. And I've got a set of coordinates written down there, X, Y, and Z. And to the right of that, I've got the same loop of wire, but drawn from the top rather than from the side. So you can see the coordinate system is rotated a bit, and we're looking at this loop of wire from the top. So we might ask ourselves, well, which part of this loop will feel a force? And the top part will not feel a force, because the top part has a current that's going the same direction as the magnetic field. And the bottom part will not feel a force. It's got a current that's going in the same direction as the magnetic field. So only the sides are actually going to feel a force. Both of those sides are going to feel the same force. It's going to be I times L times B. I is the current through it. L is the height of this loop. B is the strength of the magnetic field. So torque is the rotational equivalent of force. You probably dealt with it a little bit in 130. And torque is equal to R cross F, where R is the lever arm. It's the perpendicular distance from the axis of rotation to the point that's feeling a force. So in this case, the lever arm R is W over 2. It's half of the distance across this loop. This is distance from the middle of the loop off to one of the sides where the wire is feeling a force. And so because each of these wires is feeling the same force, it'll also be feeling the same torque. And so the total torque acting on this loop is W over 2 times ILB plus W over 2 times ILB, which gives us current times width times height times the magnetic field strength. Well, the width times the height is just the area of this loop. And if there are multiple loops, if we have multiple loops going around many times to form a coil of wire with n loops, well, each time you loop the wire around again, it'll feel the same amount of torque again. And so the total torque felt by a coil of n loops is NIAB, where n is the number of loops, I is the current through it, A is its area, and B is the strength of the magnetic field. So that's all if the wire loop is lined up so that it's parallel to the magnetic field, as seen in the top left. But once this wire loop feels a torque, it will begin to rotate. And once it's rotated to some angle, as seen in the top right over there, the torque will no longer be the same. So the force felt by the sides of this loop will be the same. We'll have F1 and F2 pointing up and down, and they'll have the same magnitude of force, is ILB. But in calculating the torque, the lever arm is different. Because the lever arm, remember, is the perpendicular distance from the axis of rotation to the point feeling a force. And as this coil rotates through the magnetic field, that perpendicular distance changes, it decreases. And so the torque on this rotated wire loop becomes W/2 times the sine of theta, which is our new lever arm, W/2 sine theta times ILB, plus W/2 sine of theta ILB. And so we can combine those up to give us a total torque of number of loops times current flowing through them times the area of that coil, times the strength of the magnetic field, times the sine of the angle, and this is important, that angle specifically is measured relative to a perpendicular line through the loop of wire. It's measured relative to the area vector of that loop of wire, as we've seen previously when dealing with Gauss's law. So theta is measured between the area vector of the loop and the magnetic field direction. Now this is all well and good. We've got an expression for the torque on this coil of wire in a magnetic field. But our coil of wire is going to act very similarly to a magnetic dipole placed in a magnetic field. Magnetic dipole will align with the magnetic field. It'll feel a torque until it's aligned, and then it will feel no more torque. And our loop of wire will also feel a torque until it's aligned with that magnetic field, until its area vector is pointing in the same direction as that magnetic field. At which point the sine of theta will be 0. It'll feel no more torque. And once it's aligned like this, it'll stop feeling a torque. And so because of these sort of very similar properties between this coil of wire and a permanent magnet, we can define a magnetic dipole moment, which would normally be used to represent a magnetic dipole, like a permanent bar magnet. On a permanent bar magnet, this vector would point from the south pole to the north pole, and its magnitude would indicate the strength of that permanent magnet. In this case, the magnetic dipole moment, which is given by this vector Greek letter mu, is defined as NIA, where N is the number of loops in that coil of wire, I is the current passing through them, and A is the area vector. And so with that magnetic dipole moment defined, we can write the torque in terms of the magnetic dipole moment and the magnetic field, as torque is equal to magnetic dipole moment as a vector, crossed with magnetic field as a vector. This torque equation will also apply to, again, a permanent bar magnet, which is a magnetic dipole as well. So magnetic field causing a torque on current loops has many important uses. One of the most important, probably the most important, is in motors. So motors are essentially coils of wire, often with many windings that are allowed to rotate about their axis and that are placed in a magnetic field. And current is run through those coils of wire. And when current is run through them, they feel a torque. And they will rotate due to this torque until their magnetic dipole moment aligns with the magnetic field, at which point generally they won't feel any more torque. And if left to their own devices, they will sort of settle down and align with that magnetic field. However, if the current is reversed through that coil of wire, then the magnetic dipole moment will also reverse and point in the other direction. And it will once again be a torque on that coil of wire. And so it will continue to rotate if the electric current flowing through the wire can be reversed with the proper timing. And there are a couple of ways to get that proper timing for reversing the current. One way is through the use of brushes in a DC motor. They allow you to hook up something like a battery to your coil of wire without them actually being physically connected, so that the coil of wire is able to rotate and connect alternately to the positive terminal of the battery or the negative terminal of the battery, switching off depending on the position of the coil of wire. And this lets you maintain torque by essentially automatically switching the magnetic dipole moment with the proper timing. A system like this, a system like brushes, can be avoided entirely by instead using an AC motor, which has a constantly varying current that reverses on its own. So when AC is put into a motor, the current will constantly reverse, and therefore the magnetic dipole moment will constantly reverse itself and give you consistent torque. Another really important use of torque on coils of wire is in galvanometers, which we've seen are the core of both ammeters and voltmeters. So in a galvanometer, you have a coil of wire in a magnetic field, usually created by two poles of a permanent magnet. And attached to that coil is a needle, which points in a certain direction depending on how the coil is rotated. And also attached to that coil of wire is a torque spring, a spring that creates a torque depending on how much it's rotated. A torque spring like this will feel a torque that's proportional to how much it's rotated, in just the same way that a sort of linear spring will feel a force that's proportional to how much it's stretched or squished. So in equilibrium, the torque supplied by the magnetic field is equal to the torque supplied by the torque spring. And so the displacement of the needle, given here by phi, is directly proportional to the current passing through the coil of wire. And so you can use a galvanometer like this to measure very small currents. The displacement of the needle will be proportional to the current running through it. I should also note that there's this sign of theta dependence, where theta is the angle between the area vector of the coil of wire and the magnetic field. That theta dependence can be largely reduced or eliminated by using a properly shaped iron core that will essentially route the magnetic field through the center of the coil of wire in sort of a consistent direction. So you won't have as much of a theta dependence. You can get that direct linear relationship between displacement of the needle and the current running through the wire.